Our deep dive today is focused on a really fascinating exploration of chemistry, specifically the world of metals and nonmetals.
We really do take the physical materials around us completely for granted. You might look at a steel beam or a gold ring and just assume it's a static, lifeless object.
I mean, I certainly did before reading into this.
Right. But when you look closer at the chemistry, you realize these elements have incredibly dynamic personalities. They're constantly interacting, fighting for atomic balance, and sometimes literally exploding when they end up in the wrong environment.
Okay, let's unpack this, because we need to start by setting a baseline for how we normally think about the world. When you think of a metal, you probably think of something hard, shiny, and conductive, right?
Like a copper wire or an iron skillet.
Exactly. And when you think of nonmetals, you probably picture dull, brittle solids or maybe invisible gases like oxygen and nitrogen. That is the classic everyday assumption. But I learned something today that totally broke my brain and threw all those assumptions right out the window.
Oh, the exceptions to the rule are the best part.
There really are. Here's where it gets really interesting. Take ductility. That's the ability for a material to be drawn out into a thin wire. I found out that a single gram of pure gold can be drawn into a wire 2 kilometers long.
Just try to visualize the physical reality of that. 1 tiny gram of gold, which is roughly the weight of a small paper clip, stretching across a distance of 2 entire kilometers without breaking.
It's insane.
It completely shatters the idea of a solid metal just being a rigid, stubborn chunk of matter. It speaks to the incredible flexibility of the atomic structure in certain elements. The atoms can just slide past one another while maintaining their bond.
And it gets weirder than that. We assume metals have high melting points, right?
Okay.
Because we use them for cooking vessels and car engines.
Sure.
But there are 2 metals, gallium and cesium, that have such ridiculously low melting points that if you simply placed a solid piece of them in the palm of your hand, the ambient heat from your own body would cause them to melt into a liquid puddle right there on your skin.
Which is such a wild visual. And what about hardness? You think of metals as tough, unbreakable things. But alkali metals, specifically lithium, sodium, and potassium, are so soft you can easily slice right through a solid block of them with a regular butter knife.
A butter knife, which perfectly illustrates why chemists cannot classify elements by physical properties alone.
Absolutely not. There are just too many wild exceptions that break the standard rules. You mentioned earlier that nonmetals are usually dull. Well, iodine is a nonmetal, but it has a very distinct lustrous shine to it.
Oh, right.
And then consider carbon. Carbon is a nonmetal, but it exists in different allotropes, which means it can take on different physical forms in nature. One of those forms is graphite, which is so soft we use it to write on paper, and it actually conducts electricity.
But another allotrope of that exact same element is diamond.
Exactly. The hardest natural substance known to humanity. It has an incredibly high melting and boiling point. Same exact element, entirely different physical reality.
So what does this all mean for you, the listener? Just look around the room you're in right now. The rigid physical categories we try to force the universe into are actually full of bizarre, rule-breaking exceptions. A metal isn't always hard, and a nonmetal isn't always fragile.
Right.
But that raises a big question. If we can't trust what a material looks or feels like, how do scientists actually know what they're dealing with?
To truly understand these elements, we have to look entirely past the surface. We have to look at their chemical reactivity. That means observing how they behave and adapt when they encounter other substances, like air, water, or acids.
So putting them to the test.
Exactly. That is where their true nature or their personality is revealed. Chemists organize this using what's called the reactivity series. It's essentially a hierarchy of elements arranged in order of their decreasing chemical activity.
As I was looking at this reactivity series, I couldn't help but think of it like a cast of characters in a movie. On one end, you have the absolute drama queens, and on the other end, you have the stoics.
I love that analogy.
Let's start with the drama queens at the very top of the list, potassium and sodium. If you drop a piece of potassium or sodium into a beaker of regular cold water, the reaction is violent. It gives off a massive amount of heat. It's highly exothermic.
Very highly.
In fact, it's so energetic that the hydrogen gas produced by the reaction instantly catches fire. They actually produce a fiery explosion just on contact with cold water.
Let's break down the mechanics of why that happens. Exothermic doesn't just mean it gets warm. It means the chemical reaction is releasing a massive amount of stored energy into its surroundings.
Right.
When sodium hits water, it desperately wants to bond with the oxygen in the water. It rips the water molecules apart so violently to get to that oxygen that it releases all this excess energy as heat. The leftover hydrogen atoms from the water bubble up as a gas, and the heat from the reaction is so intense it ignites that hydrogen gas in midair.
That is terrifying. So how do you even store something like that safely? If it reacts that violently with a bowl of water, wouldn't it react with just the normal humidity in the air?
It absolutely would. Because of that extreme high drama, they are massive liabilities if left exposed on a shelf. To prevent a laboratory from literally burning down, sodium and potassium must be stored entirely immersed in kerosene oil.
Kerosene. Wow.
Yeah, the oil creates a physical barrier that moisture and oxygen from the ambient air simply cannot penetrate.
Incredible. Okay, so that is the top of the hierarchy.
Yeah.
And then on the complete opposite end of the spectrum, the bottom of the reactivity series, you have the Stoics. Gold and silver. You can take a piece of gold, heat it to incredibly high temperatures, blast it with pure oxygen, and it just sits there. It simply refuses to react.
Which is precisely why gold retains its brilliant shine for millennia. You can pull a gold coin out of a sunken shipwreck after 300 years and it still looks perfect.
Still unbothered.
Completely unbothered. But between the explosive drama queens and the unbothered Stoics, we have what you might call the double agents. Normally, when metals react with oxygen, they form what we call basic oxides. And when nonmetals react with oxygen, they form acidic oxides.
Let me pause you there just to make sure I'm tracking the terminology. What do basic and acidic actually mean for the material in a practical sense?
Great question. It has to do with how they neutralize other chemicals. A basic oxide will react with an acid to neutralize it, turning it into a harmless salt and water. An acidic oxide does the opposite. It reacts with a base to neutralize it into salt and water.
Okay, so they usually stay in their lanes.
They do. But certain metals in the middle of our hierarchy, specifically aluminum and zinc, form what are called amphoteric oxides.
Amphoteric oxides, meaning they play both sides.
Exactly. These specific middle oxides can act as both acids and bases. If you introduce them to a strong acid, like hydrochloric acid, they act like a base and neutralize it. But if you introduce them to a strong base, like sodium hydroxide, they flip their behavior. They act like an acid and neutralize that too.
That is amazing.
They literally adapt their chemical behavior depending entirely on what they are confronted with.
That is a brilliant survival mechanism for an element. But wait, I want to go back to gold for a second. If gold is so incredibly stoic and it refuses to react with oxygen or heat or everyday chemicals, how does a jeweler ever reshape it? Or, better yet, how does a con artist manage to steal it if it's virtually invincible?
That brings us to the con artist's best friend. Have you ever heard of a substance called aqua regia?
Royal water. Yes, I was reading about this in the sources.
It is a truly fascinating concoction. Aqua regia is a freshly prepared fuming liquid made by mixing concentrated hydrochloric acid and concentrated nitric acid in a very specific 3-to-1 ratio.
Yeah.
Now, neither of those acids can put a dent in gold on their own. You could drop a gold ring in a beaker of pure hydrochloric acid and nothing would happen. But when you combine them in that precise 3-to-1 ratio, they form an extremely corrosive reagent that breaks down the stoic nature of gold completely.
Wow.
It's one of the only liquids on Earth that can dissolve gold and platinum.
There was this unbelievable historical anecdote I came across about how this was used on the streets. There's a story of a man who used to go door to door posing as a goldsmith. He would target people, usually women with older jewelry, and promise he could bring the bright original glitter back to their old, dull gold bangles.
A classic scam.
Right. So a woman hands her jewelry over, and he dips the bangles into a special solution he carries with him, which was aqua regia. When he pulls them out, they are sparkling like brand new. But what the woman didn't realize until much later was that the weight of her bangles had been drastically reduced.
It's a devious use of chemistry. He wasn't cleaning the gold, he was literally dissolving the outer layer of it right into his liquid solution.
Unbelievable.
He handed back the lighter bangles, walked away with the solution, and then later extracted the pure gold he had stolen right out of the liquid. He knew exactly how to manipulate the one chemical vulnerability of an otherwise unreactive metal.
Okay, so we've explored how metals react with water, air, and acids. But here's where we need to get to the very core of how our world is held together. How do metals and nonmetals interact with each other? Because they aren't just sitting in isolation. This brings us to the atomic give and take.
This is where we have to look at the electronic configuration of the atoms themselves. Every element in the universe essentially wants to achieve stability.
And what does stability look like at the atomic level?
In chemistry, stability usually means having a completely filled outermost shell of electrons, just like the noble gases like helium or neon have naturally. Now, metals like sodium or magnesium typically have just 1, 2, or 3 electrons sitting in their outermost shell.
So they have just a few extra hanging around.
Exactly. They are so close to the layer beneath it being full that to achieve stability, their easiest path is to simply lose those few extra electrons. When a neutral metal atom loses a negative electron, it becomes a positively charged ion, which we call a cation.
And the nonmetals are in the exact opposite situation, right?
Yes, and that's the beauty of it. Nonmetals, like chlorine or oxygen, are very close to having a full outer shell. They are usually just short by 1 or 2 electrons. They desperately want to gain electrons to fill that gap.
They're looking for exactly what the metals are throwing away.
Precisely. When they gain those electrons, they become negatively charged ions known as anions. So when a metal atom meets a nonmetal atom, you have a perfect, mutually beneficial relationship. The metal gives away its extra electrons, and the nonmetal gladly takes them.
So to visualize this for everyone listening, imagine sodium hands off an electron to chlorine. Suddenly you have a positively charged sodium ion and a negatively charged chloride ion sitting right next to each other. And just like the positive and negative sides of two magnets, opposites attract, and they lock tightly together.
That is the perfect analogy. They are held together by very strong electrostatic forces of attraction. This forms what chemists call electrovalent or ionic compounds. The most famous example is sodium chloride, which is just the everyday table salt sitting in your kitchen. What's crucial to understand is that a single grain of table salt isn't just one sodium atom and one chlorine atom. It exists as a massive, repeating, three-dimensional grid of oppositely charged ions locked in a tight, rigid structure.
And that invisible atomic structure completely dictates how the material behaves in the real world when you hold it. Because those magnetic-like electrostatic forces are so strong, ionic compounds are generally hard, brittle solids.
Very brittle.
If you take a chunk of rock salt and hit it with a hammer, it doesn't bend or dent like a piece of ironwood. It just shatters and breaks into a million pieces because you force those tightly aligned charges to shift and repel each other.
Exactly.
And they have very high melting and boiling points because you have to apply a massive amount of heat energy to finally break that strong interionic attraction.
This raises a really fascinating point about conductivity, though. We established early on that metals conduct electricity well. But what about these ionic compounds? They are made of charged ions, so shouldn't they carry an electric current?
This was one of the coolest quirks I discovered in the research. I want you, the listener, to picture this. If you take a pile of solid, dry table salt and hook a battery up to it, it'll absolutely not conduct electricity. The current stops dead.
Because it's locked in place.
Exactly. The charged ions are locked in that rigid grid structure. The charge has nowhere to move. But if you take a blowtorch and heat that salt up until it melts into a liquid, or much easier, if you just stir that salt into a glass of water to dissolve it, everything fundamentally changes.
The water molecules physically pull the sodium and chloride ions apart?
Yes, the electrostatic forces are overcome, the ions are suddenly free to float and move around in the water, and boom, the solution conducts electricity beautifully.
It is a brilliant demonstration of how a material's physical state completely alters its chemical properties. The raw ingredients in the glass are exactly the same as the dry salt, but simply granting those atomic particles the freedom of movement changes the entire nature of the substance.
Okay, so we understand how they behave in the lab, and we know how they bond together like magnets at the atomic level. But let's look at the real world. All these metals, the iron in the framework of our buildings, the copper inside our power cords, the aluminum in our soda cans, they all originate in the Earth's crust.
They do.
They exist buried in the dirt as minerals and ores. Iron there mixed with tons of useless rock and impurities, which miners call gangue.
Yeah, ging is essentially all the earthly garbage, the sand, the soil, the rocky material that is physically attached to the valuable metal ore when you dig it out of the ground.
So how do we solve this ancient puzzle? How do human beings actually get the pure metal out of a useless rock?
It all circles right back to that reactivity series we discussed earlier. The method we use to extract a metal is entirely dictated by how reactive it is. It's a very precise hierarchy. Let's start with the easiest ones. The metals of low reactivity, towards the bottom of the series. For example, mercury is found in nature as a reddish ore called cinnabar, which is chemically mercury sulfide. Because mercury has such low reactivity, breaking its bond is incredibly simple. You just heat the cinnabar rock in the open air. This is a process called roasting.
Just throw it in a fire.
Pretty much. The heat naturally converts the sulfide into mercuric oxide, and if you just keep the heat on it, the oxygen eventually gives up and strips away, leaving you with a puddle of pure liquid mercury.
So for the low reactivity stuff, we just apply brute heat. But what about the metals right in the middle of the pack? Things like zinc, iron, and lead. They aren't going to give up that easily.
No, they definitely won't. Those moderately reactive metals are usually found locked away in the earth as either sulfides or carbonates. You can't just throw them in a fire to get the pure metal. It requires a clever two-step process.
Step one.
First, you have to convert them into metal oxides because chemically it's much easier to extract a pure metal from an oxide than a sulfide. Now, the way you create that oxide depends on the rock. For sulfide ores, you heat them strongly in the presence of excess air again, the roasting process. But for carbonate ores, you heat them strongly in a severely limited supply of air, which is a process called calcination.
Let me pause you there to make sure I'm following the logic. So if the metal is mixed with sulfur, we blast it with plenty of air and heat it. But if it's a carbonate, we intentionally starve it of air while we heat it.
Exactly. In both cases, the goal is exactly the same. We are just trying to force the metal to drop whatever it's currently holding and bond with oxygen instead. Once we have a metal oxide, we move to step 2. We need to strip that oxygen away to leave the pure metal.
How do we do that?
We introduce a chemical reducing agent, typically carbon. When you heat the metal oxide along with carbon, the carbon basically acts like a thief. It steals the oxygen away to become carbon monoxide gas, which floats away, leaving the pure solid metal behind.
Okay, so that handles the middle tier. What about the absolute top tier? The highly reactive drama queens we talked about earlier, sodium, magnesium, calcium, and aluminum.
Carbon won't work for them at all. Those metals have a much higher affinity for oxygen than carbon does, so carbon simply isn't strong enough to strip the oxygen away. They won't let go. For these highly reactive metals, we have to use the pure brute force of electricity. This is called electrolytic reduction.
How does that work in practice?
Think of it like a highly polarized magnet pulling a locked team apart. We take the molten metal compounds and run a strong electric current directly through them in a vat. The pure metal gets dragged over to the negative side of the circuit, the cathode, and collects there. Meanwhile, the non-metal component, like chlorine gas, gets pulled away and bubbles off at the positive side, the anode. We are literally tearing the compound apart with electricity.
That is brilliant, using their own intense reactivity against them. But speaking of brute force, I have to highlight my absolute favorite detail I uncovered about extraction. The thermit reaction.
Oh, this is a good one.
Sometimes, instead of using carbon as the thief, chemists use a highly reactive metal to displace a less reactive one. There's a process where they react iron oxide with pure aluminum powder. Aluminum is higher on the reactivity series, so it violently steals the oxygen from the iron. This displacement reaction is so highly exothermic it releases such an intense explosive amount of heat that the pure iron produced isn't just warm, it is literally birthed in a molten liquid state.
And the real-world application of that is wild.
It's unbelievable. They actually use this violent, fiery chemical reaction on location to weld cracked railway tracks together. Picture being out in the middle of nowhere on a train track. Instead of bringing a massive welding machine, engineers just set up a crucible of iron oxide and aluminum powder right over the crack, ignite it, and let the sheer heat of the chemical reaction pour newly formed liquid iron directly into the gap to seal the track.
It really paints a vivid picture of human ingenuity. We use the violent inherent energy of these elemental interactions to build the literal infrastructure of the modern world. But of course, once we extract these pure metals and build our bridges and trains out of them, a brand new problem begins.
Yes, the endless battle against time. As soon as we spend all this energy pulling these pure metals from the earth, the natural elements in the air are immediately trying to pull them back into compounds. The enemy here is corrosion.
Exactly. Nature always wants to return to a stable state. When pure metals are exposed to moist air, they degrade. Silver slowly reacts with sulfur present in the air to form a dull, black coating of silver sulfide. Copper reacts with moist carbon dioxide in the air to gradually form a green coat of basic copper carbonate.
Which is exactly why the Statue of Liberty is green. It's made of copper, but over a century in the New York harbor, air gave it that massive basic copper carbonate shell.
That is the quintessential example. And then, of course, there is iron. When iron meets both air and water, it oxidizes to form that flaky brown substance we all know as rust.
And rust is absolutely devastating for infrastructure. It weakens steel beams and rots out car frames. So human ingenuity steps in again.
Yeah.
We fight back against corrosion. There are simple methods like painting, oiling, and greasing to create a physical barrier.
Right.
There is galvanization, which is a really clever method where we coat steel and iron with a microscopic layer of zinc. The zinc actually sacrifices itself to the environment to protect the iron underneath, even if the coating gets scratched. But the absolute most important weapon we have against corrosion, and honestly, for making metals useful in our everyday lives, is the ancient art of alloying.
Alloying is fundamental to modern civilization. Very few metals are actually used in their completely pure state because pure metals often lack the necessary physical properties we need them to have.
Here is a perfect everyday example for you listening. Think about a shiny gold ring or a gold necklace. Pure gold is known as 24-karat gold. But if you walk into a jewelry store, almost nothing is 24-karat. Why? Because 24-karat gold is completely unsuitable for making jewelry. It is simply too soft. If you wore a pure gold ring, it would bend, scratch, and deform just from you gripping a steering wheel. So what do jewelers do? They create 22-karat gold.
And to do that, they melt down 22 parts of pure gold and alloy it. Mix it with 2 parts of either silver or copper. That tiny, seemingly insignificant addition of another element fundamentally changes the atomic grid structure, making the gold suddenly hard enough and durable enough to wear every single day.
It almost sounds like alchemy, but it's just really precise science. An alloy is a homogeneous mixture of 2 or more metals, or sometimes a metal and a non-metal. You melt the primary metal down, dissolve the other elements into it in very specific proportions, and let it cool. And the resulting properties are entirely different. Give me some more examples of everyday alloys we rely on.
Think about iron. Iron is the most widely used metal on the planet, but pure iron is surprisingly soft, and it stretches easily when it gets hot. But if you melt it and mix in just a tiny fraction of a percent of carbon, about 0.05%, it becomes incredibly hard and strong. We call that steel.
Which changed the world.
Completely. And if you take that iron and mix it with nickel and chromium, you get stainless steel, which is incredibly hard and utterly refuses to rust, which is why your kitchen silverware doesn't degrade.
And it's not just about making things stronger, right? Sometimes alloying is about intentionally altering conductivity or melting points.
Right. Pure copper is a fantastic electrical conductor, which is why it's inside all our electrical wiring. But if you alloy copper with zinc, you get brass. If you alloy copper with tin, you get bronze. Both brass and bronze are much worse electrical conductors than pure copper, but they are fantastic for casting into shapes and machining into musical instruments or statues.
And there's solder, too.
Yes, if you alloy lead and tin together, you get solder. Solder is engineered to have a purposely low melting point, so an electrician can easily melt it with a small hand tool to permanently weld electrical wires together without melting the wires themselves.
It is wild to realize that almost every single metal object you touch throughout your day is a highly engineered, deeply considered recipe. And what's truly crazy is that human beings have been mastering this for a very long time. I want to bring up this absolutely incredible historical marvel. Have you ever studied the Iron Pillar in Delhi?
The iron pillar is an absolute masterclass in ancient metallurgy. It defies what we think of as modern technological superiority.
It really does. For those listening, this is an iron pillar located near the Qutub Minar in Delhi, India, built over 1,600 years ago. It stands 8 meters high and weighs a massive 6 tons. Now, think about what we just said about iron and rust. This pillar has been sitting completely outside, fully exposed to the harsh Indian summers and brutal monsoon rains for 16 centuries. And yet, it hasn't rusted away into dust. The ancient Indian ironworkers somehow developed a brilliant metallurgical process that formed a protective microscopic film over the iron, fundamentally preventing it from corroding centuries before modern chemistry labs even existed. Scientists and metallurgists from all over the world still travel there to study it today.
It is a humbling reminder. It shows us that understanding, manipulating, and perfecting the properties of metals isn't just some modern laboratory science. It is an art form deeply embedded in human history and the very development of our civilization.
That is beautifully said.